Hello, Marco here. Welcome to another tutorial of the From Scratch series. So far, we have covered ground vehicles and we created a car and a motorbike. And more on the physics side, we created a hover vehicle. Now it's time to cover flying vehicles. And I would like to start with a helicopter. So this is in a nutshell what we are going to build. In this tutorial, for time reasons, we are not going to add the engine sound, but that's relatively easy to do. And you can follow my other tutorial on adding the motorbike engine sound, and something similar can also be done for the helicopter. Also, if you don't have time to follow the tutorial and code yourself, you can find the fully ready-made project with the engine sound included in the description to this video. And you can get it for a small fee, which helps me keep this tutorial going. So without further ado, let's get started. Let's open the Epic Launcher. Go to Library and launch Unreal Engine 5 Early Access 2. Once the engine has loaded, we go to Games, Blank, and enter a name for our project. Let's call it Kinematic Helicopter. And click Create. Once the engine has loaded, we just dismiss the new plugins available pop-up, which we don't really need. And let's start by clicking onto the player start and then pressing the delete key to remove it from the level. The other thing we want to do is click on the floor static mesh, and let's make it a bit larger so we have more space to fly around. So let's give it a 20x and 20y. With that done, let's go to the content folder. Right click and add a new folder, and let's call the new folder helicopter. And now with the folder selected, we click on the import button, and you can go to the folder where you downloaded the project assets, which are available from the description. In my case, they are inside Documents Blender. So let's select the low poly helicopter FBX and click open. Then very important, click on skeletal mesh to force this to be imported as a skeletal mesh. The reason is that we have not rigged the helicopter directly in Blender, but we are using the parenting trick, which makes Unreal then treat it as a skeletal mesh and create the bones for us directly. Very handy trick. So click skeletal mesh and then import all. Never mind this message, we don't have any bind post, that's fine. And you can see below our helicopter as it's just been imported. We can open skeletal mesh just to have a look. And if you check the bone structure, basically we have a root bone for the body. And then we have a bone which is used to rotate the main rotor. And then we have another bone for the tail rotor. And note that they have two different rotational axes. So the main rotor is rotating around, and we can see it better if we click. The movement tool rotates around the blue axis, which is the Z axis, and the tail rotor rotates around the green axis, which is the Y axis. So we should keep this in mind later on for the time that we do the animation. Okay, this is pretty much it for importing the helicopter. Now to make things a bit more interesting, we also want to import a helipad where we can land onto. So let's click again on content, create a dedicated folder just to keep things a bit separated, helipad, and then import. And the asset is named helipad.fbx. Click open. And this time this is not a skeletal mesh, so we can leave everything as is, just click import all. And we should get our helipad. And since we added it, we can also position it somewhere on our floor mesh, for example here, so we can later on fly to it and try to land onto it. Okay, let's click Save All just to make sure. And by the way, we will also be asked how we want to save the level, which we're working on. So under Content, we want to right click and create a new folder, which is called Maps. And then we can call the level Test Level. Now, also very handy when you open the project, Unreal by default will load an empty level, but we can force the editor to work with our current level. So under Edit, Project Settings, under Maps and Modes, instead of default template, we select our test level. And then just close this window. Okay, we are ready to start working on our helicopter. To do that, let's right click on Content, New Folder, and as usual, let's call it Blueprints. Then within the Blueprints folder, we right click, Blueprint Class, and we want to work with a pawn because we're going to control it. Let's call it BP Helicopter. And then double click to open it. First thing that we want to do is to add our helicopter skeletal mesh. So we click on Add with the root selected, and we type skeletal mesh. So let's call this helicopter, a bit of lack of fantasy. And now we drag it onto the default scene root so it replaces it. Perfect. Now with the helicopter selected, we go here on the right side, and on the drop down, we find our low poly helicopter. We can select it. So now the helicopter is assigned to be the skeletal mesh used for this skeletal mesh component. Let's compile for the moment and save and check a couple of things back into the helicopter asset. So if we go into the folder here, there are two things that we want to do. The first one is right click on the low poly helicopter skeletal mesh and create anim blueprint. Just give it a default name, it's fine. It's not the perfect name, but we can live with it. The other thing we want to do is to open the physics asset. So double click on it to open it. And as you can see, the physics asset is a bit weird. So we don't want any of these physics bodies that have been automatically created. What we want to do is right click on the first one, body, and then select delete all bodies below. With that done, we don't see anything anymore here. So we go here onto this little gear icon and select show all bones. Okay, with that done, we want to assign a physics body. Actually, we want to create the physics body for the root bone, so body bone. And we do it by selecting the bone and then going here on the right under tools, we select single convex hull and leave everything else as is, and then click on this green add bodies button. And as you can see, the engine has created physics body for us. And that looks pretty good. So we have encompassed all the parts of the helicopter that typically might collide with something. So we are good to go here. Let's just click save, and then we can close the physics asset. Okay, let's go back to our helicopter blueprint, open it, and clicking on the root component, which is now our skeletal mesh, we click add, and we're going to add a spring arm to it. And as usual, we click on the spring arm, click add again, and let's add a camera. So this will be a camera that helps us to see our helicopter in game. And as you can see, the spring arm is a bit too short. We will start by raising the position of the spring arm around 100, and you can read the value in the tooltip below. And now when it comes to the length, because the helicopter is pretty long, we enter 1100, so 1100. And that will place our spring arm on the tail of the helicopter. And then by clicking the rotate tool, we want to give it maybe the 10 degrees upward pitch. So we can look down at the helicopter like that. Also, let's not forget to click on the root and make the pawn automatically process by selecting auto process player and selecting player 0, which is perfect. And last but not least, we want to click again on the skeletal mesh and then make sure that we have collisions. Otherwise, the helicopter is going to go through the ground. And as you can see, by default, I scrolled under details, collisions. Collision preset is set to no collision. We want it to be block all. That also helps us to position the helicopter on the floor. So compile and save. And let's close this for the moment. And now we can take our helicopter from the content browser and drag it onto the floor. And then you see that it's inside the floor. I can drag it up, and then with the End key on my keyboard, it will be placed exactly flush to the floor, as you can see. Here we also have a preview of our camera in the bottom right corner. And yeah, it shows that we have a view of the helicopter from the camera attached to the spring arm. Now it's time to add some functionalities. So let's open again our helicopter blueprint. And we will not need the event begin play and the event actor begin overlap. So we can just select them and delete them with the delete key. And as usual, before we add any code, we need to make our helicopter controllable by the player. And that entails adding some input events. So we go to Edit, Project Settings, and when we scroll down under Engine to Input. The helicopter is a pretty complicated machine to control, so we're gonna have 4 input axes. One is to go forward and backward, another one is to go left and right, another one is to go up and down, and the last one is to rotate around the EO axis, so the vertical axis of the helicopter, which allows us also to choose a certain direction. So let's start with axis mapping, press plus, and then let's call this axis forward, backward, because we are controlling the movement, forward, backward movement of the helicopter. And then let's use the W key. So what I've done is I've pressed on this little keyboard icon and then press W on my keyboard, and that automatically selects the key. Then we press plus again. Again, we press on the little keyboard and press S. That's for the backward. And let's remember that being backward, we need a -1 in front of it. Then we add another axis with the plus. And this time we call it right, left. And I'm using right, left because right is positive and left is negative. So we don't forget this is the same as forward, backward. So right, left, we want to use the D for right. And then I'm going to add another key and use the A for left. And let's remember to change this to -1. Now, let's add the up-down axis. So I'm going to do the same thing, press again on the plus close to axis mappings, and we're going to call this up, down, and up is positive and down is negative. So we're going to use this time the arrow keys. Okay, so I can still click the little keyboard button and then press my up arrow key, and I get the up key, and then plus again to add the second key. Click, press the down, and the down will be -1. Last but not least, when it comes to the movements, we want to add the axis for the EO rotation. Okay, so we'll call this one EO rotation, and the positive rotation is going to be with the right button, and actually positive meaning clockwise. And then we add another key, the plus, and we assign it to the left arrow button, and this one is going to be counterclockwise. So we'll add a -1 for it. Okay, so this is everything we need for the movement of the helicopter. So we have the 4 axes. And since we want to control also the spring arm, we're going to add other 2 axes. And I know that this makes it a bit complicated, but will be handy to see how our helicopter is moving and to also land more precisely. So we're going to press the plus again and do a look up. And for the look up, this time we have to use the mouse. So we're going to use the mouse Y. And then we add yet another axis, the last one. And we will call it look right. And for it, we will select the mouse X. Okay, so this is all for what concerns the inputs. Now we can use them to handle our helicopter. So let's go back to coding and close this window. And now we are in the event graph. Okay. Let's start by adding the handling of the input events we just created. So you right-click on the event graph and let's type the forward-backward axis event. And since we already did, we're going to add them all because the code is pretty similar. And then we use the right, left event. And then we scroll down and then we use the up and down event. And last but not least, scrolling down, we're going to use the U rotation event. Okay, so we have our event tick, which I'm going to drag a bit up just to make room. We'll fill this in later. And now we have our 4 input events. So let's start with the first one, which is the forward backward, and I'm zooming in using the mouse wheel. We'll take the axis value, which is in the range 1, -1 or -1, 1, coming from the 2 keys we have associated to it, W and S. And by the way, you can also associate the gamepad, for example, if you want to. So we take this axis value and we multiply it by a factor, which is a sort of conversion rate between the axis value, which again is in the range -1 and 1, and the forward-backward speed of the helicopter. So once we have created the multiplication node, and you can get that one by pressing the asterisk, we want to right-click on the second pin, which now says 0, and click on Promote to Variable. And we're going to call this FB as forward-backward speed factor. Okay. Now, since we don't want to forget that we want to assign a value to it, I need to compile before I can do that. Now I can assign the default value to it, and we're going to use 600. So this is 600 centimeters per second. That's the speed that we will get for a positive forward speed and -600 for a negative one at this point. You are free to play with this value so that your helicopter moves faster or slower depending on your game and depending on what you like. Now, with the output of this multiplication, we're going to right-click and select the FinTerp 2 node. Now, why we want to do that is because we want our helicopter to move in a way that resembles a real helicopter, so you don't have immediate transition, from backward to forward movement and vice versa, and it's the same for lateral ones. So everything has to be gradual. And thinking gradual movement in kinematic terms, not in physics terms, it means using interpolation. So we're going to use the FinTerp 2 node, and we connect this to the target because that's what comes from the user input. So that's what we want for target. And now for current, we want to create a variable which is tracking the current forward-backward speed. So we're going to click here on the variable and we call it FB speed. And make sure that you select its type to be float. Okay. This variable, we drag it to the event graph and do a get, and we connect it to current. Delta time, just drag out of the pin and then start typing delta time, and you will see get word delta seconds. And that's the duration of the tick that the engine calculates automatically on a frame-by-frame basis. And when it comes to interpolation speed, let's use a 2 as a factor, and you can play with this one as well, depending how quickly you want the helicopter to transition from one movement to the other. Now, as usual, when we use the FinTerp2 node and we have an input as current, we need to save back the value in the same variable. So let's take the FB speed variable, drag it on top of the execution spin, which automatically makes a set. Drag it into position and connect it to the output. Perfect. So now we have exactly the handling of the input code for the forward and backward movement. We want to do exactly the same for the right and left. So in the exact same way, let's drag out of this pin asterisk to do a multiply. Right click on the second pin, promote the variable. We're going to call this RL speed factor. Perfect. And then right click, add the FinTerp2. And by the way, we could also just select get word delta seconds from above, shift click on the FinTerp2, and then Control W to duplicate that. And since we're going to need this multiple times, I'm going to do Control W and also place it here with the input axis up and down, and Control W also with the ear rotation. Okay, so we don't have to do that anymore. We have it ready. Good. So now we can take the output of the multiplication, connect it to target. For current, as you know, we need a variable to be created. So let's go under variables plus, and let's call it RL speed. So that's right and left speed. And let's drag it on top of current. So it's automatically becoming a get. That's a neat trick. So you don't have to select the get because you're connecting on top of an input. So it's a get. And then let's take the same variable, drag it on top of the execution pin to make a set. Drag it to the right and connect it. And everything else stays the same. The only thing is that this RL speed factor, we haven't set a value for it. So let's compile so we can edit it. And we're going to use a factor of 300. So in this case, you noted that our forward-backward speed is 600 and our right-left speed, lateral speed is 300. You can make them the same, but typically a helicopter might move forward and backward faster than it moves laterally. So I thought to use a value which is 1/2 of the other. Okay, that's good. We can now do the exact same thing also for up and down and the rotation. So let's give ourselves a bit of room here. Drag out asterisk to multiply, promote the variable. We're going to call this up-down speed factor. And you will note the repeating pattern that we're using here. Connect it to target. Create the variable to handle the up and down speed. Or float. Drag it on top of current so it's connected. And also drag it on top of the execution pin here. So it becomes a set, move it to the right and connect it. Note that the interpolation speed is 2 everywhere, which it's a value which you can experiment with. Again, I found that it's working fine for me. And the last one, Oh, by the way, let's not forget to give this up-down speed factor. To that, we have to compile first. And for the up-down speed factor, I'm going to use the value of 200. And this is the speed the helicopter will move up and down with. Again, you can try with different values and see what works best for you. Okay, the last one, drag out, asterisk to multiply, right click, promote to variable. We're gonna call this rot speed factor. Connect it to target, create the, oops, and you're not gonna see it because I need to scroll, rot speed variable, which we're gonna take and drag onto current and onto the execution pin. So it becomes a set, drag to the right and connect. Compile so we can give a value to the rot speed factor, and I'm going to give it a value of 100. Okay, so super quick recap. We have 4 input axes, forward, backward, right, left, up, down, and then the rotation, which is clockwise and counterclockwise. They all have the exact same structure. They all use a conversion factor, which is different for each one. So we have a nice and smooth movement for the helicopter. And for each one of them, we have a speed variable, which determines the movement we have to apply to the helicopter. And this is what we're going to do into the event tick. Okay, how do we do that? Let's zoom in and move the event tick a bit up. And we are going to start by handling the forward movement, and so forward, backward, and the right, left movement. So when the helicopter is moving forward, basically we want to use as a reference the forward vector of this actor. So we're gonna right click on the event graph and say get actor forward vector. And this is the direction. So in order to get a velocity vector out of it, we have to multiply it by the speed variable, which we handed below within the input. So let's drag out of the pin, asterisk to multiply, star to multiply. And now let's drag the forward backward speed variable onto the event graph and select a get. And then as we connect it, the pin will convert automatically to a vector times float operation. Let's leave it here for the moment. I want to go down here below it and then do also get actor right vector. The reason is that I want to combine the forward movement with the lateral movement, so that forward backward with lateral movement, so that we can slide also with a diagonal angle basically. So we have full control of our helicopter like in a real helicopter. So drag out of the return value, asterisk or star to multiply. Let's drag the RL speed variable onto the event graph, right click on get, and then connect it to the node. Okay. We are going to tweak this in a moment, and I will show you why we do it. But for the moment, let's continue without the small tweak that will be here. Okay. So what we do is we want to add these two vectors together. So we have the combined forward, backward, and lateral movement vector. We want now to do the same with the up and down movement. Okay. Need a bit more space, so I'm gonna take this full code which I've selected with the left mouse, and then I will drag it up. And here we're going to do something similar. So we say get actor up vector, and now we drag out of it, star or asterisk to multiply. Let's take the up down speed variable, drag it onto the event graph, get up and down speed, and now connect it, drag it onto the node. So it becomes a vector times float. And now we have the up vector movement as well. So we have the movement along the up and down direction. Now, remember again, we're going to have a little tweak here, but for the moment, we're just going to sum these two up. Okay. So what we are going to do is we are summing three vectors together. Okay. And you see that we have the actor forward vector times its speed, the right vector times its speed along that axis, and then the up and down vector times its speed. Okay. Now, in order to make this to work on a frame-by-frame basis and make it constant and stable at different FPSs, we want to multiply everything, so this vector, by word delta seconds, so by delta time. So I'm going to right-click here in empty space, word delta seconds. And by multiplying a speed by time, we basically obtain a displacement, okay? This allows us to determine the direction the helicopter should move toward at every frame, and we can combine this direction in any way that we want using the input along the forward and backward, right and left, up and down. Okay, so we have really full control of the helicopter along all the axes. Now, to keep track of this forward movement, let's right-click on this output node from the multiplication by get word delta seconds, and let's promote it to variable so we can keep track of that. And we're going to call it delta location. Okay, so it's clear to us and to everyone looking at our code what this vector represents. Now we can drag this up because we want to connect it to the event tick. This vector is exactly what we want to use for add actor word offset. And let's connect it. And as you can see, add actor word offset uses a delta location. That's exactly what we have calculated previously. So let's connect the two. And now to make the collisions work, make sure that you are checking the sweep flag in here. Okay. Now with this set, we are ready to test our helicopter. So let's compile and save. Mind the fact that we are handling now the movement along the three axes. So forward, backward, left and right, up and down. We are not handling yet the rotation, so we will not be able to give a direction to our helicopter. That's what we're going to do next, but we should be able to fly it around. So let's go back to the level, click play. And of course, there is also no animation of the props because we haven't built that yet. But let's see, I'm going to press the up key. And as you can see, my helicopter is moving up. I'm pressing the down key and the helicopter is moving down. Let's see if we can move to the left with the A key. And yes, the helicopter moves to the left. D key moves it to the right. W key moves it forward. And the S key moves it backward. Okay, now let's try to combine some movements so I can move up, but also move forward at the same time and also move left. Okay, so all movements are combined by the code that we just wrote. Let's also check the collision. So now if I'm going down, it should stop as soon as it touches the floor, which it does. Okay, so the collisions are also working. Perfect, time to go back to our blueprint. So ask to stop playing. Let's reopen our blueprint. And now it's time to handle also the rotations. So let's zoom in onto the event tick. And after the actor word offset, let's add another function, which is set actor rotation. Let's connect the execution pins and align them. And now we need to split this new rotation pin. So we right click and we say split struct pin. So we can handle the 3 rotational axes, the roll, pitch, and yaw independently. Let's start with the yaw because that's directly connected to the input that we created for the yaw rotation. So let's take the current rotation, right click, get actor rotation. And you find it down here. Let's also split this pin because we're only interested in the yaw rotation. So right click and split struct pin. So we have direct access to the yaw. And what we want to do is drag in the yaw rot speed, which is the speed of rotation around the yaw axis. Multiply it by delta time, so it becomes an angle, and I'm dragging out of the output pin, clicking asterisk to get a multiplication, and now I want to get word delta seconds. Perfect, and connect it. So by multiplying a rotational speed by time, so the frame duration, we are getting a rotation angle, okay? And this rotational angle, it's a delta rotation angle, and I want to add it. So I'm gonna drag out and press plus for addition. I want to add it to the current yaw rotation, and this one is going to be the new yaw rotation, okay? So very similar to what we already did with the vectors, but just acting on the yaw rotation and taking the speed, multiplying by time to get a rotational angle, which is a delta angle, adding it to the current angle, and that makes the helicopter rotate continuously based on our input. So let's compact this a little bit. Perfect, so it's neat and clean, and take into account that we are not touching for the moment the roll and the pitch, but we will do in a sec, and I'll show you why we need to do that. Okay, so let's compile and save. And let's test again, play. Okay, so now I should be able to go up, but that's exactly like before, but this time pressing the right and left arrow key should allow me to rotate the helicopter and point it to the direction that I want it to go. Now, this is not very evident because the spring arm, so the camera, is rotating with the helicopter. So to better see this, and remember we haven't added any code to handle the rotation of the spring arm for us, we could. But we could also, for the moment, for example, decouple the rotation of the spring arm from the helicopter. And to do that, just press ESC, reopen the blueprint. Now click on the spring arm, and let's untick inherit pitch, inherit yaw, and inherit roll. So the spring arm is not rotating in any direction with the helicopter. We can only rotate it manually. We'll add the code for that later, but that allows us to see the current movement and the movement that we're going to add in a second much better. Okay, so I'm going to compile and save, and now if I play again and I raise the helicopter and I press the rotation key, so you see that the helicopter is rotating as expected, and it's clockwise with the right key, and it's counterclockwise, and of course seen from above with the left key. And also you see that the movement is smooth. So if I let the key go, the helicopter keeps rotating for a bit, like it has inertia, rotational inertia, and that's what we are simulating with the interpolation. That's perfect. Note also another thing which is interesting, and it's a byproduct of how we wrote our code using the forward vector, for example. Now if I point the helicopter in a certain direction and I press the W key, the helicopter is going to travel in that direction. So basically, I can rotate the helicopter around the EO axis, and it will follow exactly the direction that I'm setting. And that is exactly how a real helicopter works, right? If you point it in a certain direction and then you move forward, it will follow that direction. Okay, so let's escape and go back to our blueprint. And now we are going to add a very nice effect, which on the other hand will create a problem, which we will solve later, okay? So what we want to do is, in a real helicopter, when you move forward, the helicopter pitches forward. So there is an inclination of the helicopter as it moves forward. And it's the same for the lateral movement, right? So when the helicopter hovers laterally, then also it's inclined a bit toward the direction of the movement. And we want to simulate this. So the way we're going to do it is by acting on the roll and pitch angle in relation to the speed of lateral movement and forward-backward movement, okay? So remember that the roll is related to the lateral speed because it's around the forward axis, and the pitch is related to the forward speed because it's around the right axis, okay? So what we want to do is drag to the event graph a copy of the right and left speed variable and do a get, and also a copy of the forward and backward speed variable and also do a get with it, okay? And now we want to multiply them both by a factor, which we'll have to determine. And basically that's the transformational factor between the speed and the inclination angle, okay? So that will require a bit of trials and error. Of course, I've already tried that when making this tutorial and preparing it, so I already know the values, but I'm going to show you how to do that. So let's drag out of the right and left speed star for multiplication. And now let's connect the output of this node to the roll angle. And let's enter here a factor of 0.016667. Okay. Let's do the same with, and by the way, we could promote this to a variable, which would be a nice thing. So let's do that after we have done the next one. Okay. So drag out star to multiply. Let's connect this to the pitch angle. And now for this factor, we're going to use a minus 0.008333. And you might realize that these factors come from actually divisions. And I've found that what works well is, to use a value which is in relation to actually the speed so that we get a nice angle, and you can play a bit with those factors, okay? Now that we have both the values, let's compile and save. And actually let's give them, some meaningful names as variables. So right click and promote to variable. When you do that, by the way, the engine will keep the value, which is a nice feature. So we'll assign that value directly to the variable you're promoting to. And let's call this RL speed to angle or to roll factor. And you can tweak it later and right click on the second one, promote to variable, and we call it FB speed to pitch factor. Okay. So we know exactly what these are and what their function is. Okay. So we are ready to test this, and as you will notice in a sec, this modification creates a problem. And the problem is, in a nutshell, that we are changing also the direction of the forward vector and the right vector in this way. And that has an implication on the code that we wrote here. So we'll need to make a little adjustment, okay? Let's try to check that. Compile and save, close, play. So let's go up in the air. And then with the arrow key, of course, we can turn. And now let me, Okay, that's a better view. Let's move us forward with a W, and you see that the helicopter is inclining. But you will also see that it's moving downward at the same time, and I'm not touching the down key, nevertheless, because this also rotates the forward vector, and we are following the direction of the forward vector. We are also moving down, and the same thing happens if I press S to move backwards. So we have now backward inclination. We're also moving down. So I will need to compensate for that, using the arrow key, but I don't want that. And we're gonna fix this in a moment. Now let's take a front view, which is also a nice one. So now if I press the D key, we're gonna move to the right, the on right of the helicopter. And then it's the same with the A key, we're gonna move to the left side. But you also notice that we are losing altitude. That's because the right vector is now inclined as well. And we're following it. So let's fix that. And the fix is quite simple. Basically, we're gonna take the forward vector and the right vector, and we're gonna project them onto the ground plane, basically. So they're always horizontal, no matter how the helicopter is inclined, okay? And the fix is actually happening on this sum, on this couple. And it's as simple as dragging out of the sum pin here and using a function called project vector onto plane. And then the output of this function, we connect it back to the sum with the up vector, which is fine. And the vector we want to project is, as we said, the sum of the forward vector times its speed plus the right vector times its own speed. And the plane we want to project it onto is the horizontal plane. And this plane is in 3D denoted by its normal, which is 0, 0, 1. So we just have to put a 1 with the Z. Yes. And maybe let's make this a bit prettier as a code. Perfect. And then now we have our fix for the movement, even though we are rotating the helicopter around the roll and pitch axis, just to make that, to give that nice effect. So compile, save, close, and play. And now let's go up in the air. And now let's rotate. Let's actually slide left, sliding right, forward, which is better seen from this angle. And as you might notice, we are not losing any altitude because the fix is projecting the vectors on the horizontal plane anyway. So we are following that direction, and that allows us also to do some nice landing. And of course, it's not easy to see this from this angle, but let's see if I'm able to land onto the platform. It takes a bit of practice, but in the end, you're able to land onto the platform. Okay, there's only one thing left to do at this point, which is to animate the rotors of our helicopter. So let's open the helicopter folder and retrieve our animation blueprint. And by the way, remember that we have not assigned it yet to the skeletal mesh, so maybe we should do that. Last step. So let's reopen the helicopter blueprint, click on our helicopter skeletal mesh, and on the right, under animation, make sure that animation class is our low poly helicopter skeleton animation blueprint. Let's compile and save. And of course, nothing happens at the moment because we have written no animation code whatsoever, but we're going to do it in a sec. So let's close this and we go back to the helicopter folder, open the animation blueprint for our helicopter. And let's start by going into the event graph. And as you remember, animation blueprints always have an event graph and an anim graph. So the anim graph will handle in a sec. Let's start with the event graph. Okay. We want to do a couple of things. So we're going to take this try get pawn owner node and we're going to drag it up because we want to add another event. So what we are doing is, instead of passing values to the animation blueprint from the helicopter blueprint, like we did in the previous tutorials, this time we are doing the other way around, which is also possible. So we are retrieving the owning pawn from the animation blueprint, and we're going to get a reference to it. Okay. So the right way to do it is to use an event which is called blueprint initialize animation. So we right click and we search for initialize animation. So event blueprint initialize animation. And now we use the try get pawn owner and we cast it to our BP helicopter to check if the owner is the BP helicopter, which it should be. And if the cast is successful, let's right click on SBP helicopter, promote to variable, and let's call this ref to helicopter. Okay. Now that we have a reference to our helicopter BP, which is owning this animation blueprint, we can use that to retrieve the values that we need to animate the rotors. And these values are based basically on the speed of the helicopter with some nice effects, which I will show in a moment. So let's go down where the event blueprint update animation is, and let's drag a reference to our helicopter, the one we just created. And from it, we're going to retrieve the 3 speed values, which we are very familiar with by this time. If I drag out of this, because it's a BP helicopter, I have access to FB speed. So get FB speed. I drag out again and I have access to up down speed. Get up down speed. And last but not least, I'm going to drag out and get access to the right left speed. Perfect. Now what we want to do in order to have a nice effect on the speed of the rotors, and here we are working on the main rotor. We're going to work on the tail rotor in a sec, but let's start with the main rotor. We want the speed of the main rotor to be determined by a combination of, how fast we're moving forward, backward, up and down, and right and left. So you can imagine that if you're powering the engine of the helicopter to make all these movements, the main rotor is going to rotate a bit faster depending on that, but otherwise it has its base rotational speed. Okay. Now, not all these movements we want to affect the rotor in the same way. So for the forward and backward speed, we're going to use an abs function. And the reason is that we don't want the rotor to slow down just because the helicopter is moving backward. And remember that that value of speed is negative. So we're going to take the absolute value, which always makes it positive. Now for the up and down, we want the rotor to speed up only if the helicopter is moving up. But if it's moving down, we're kind of landing, for example, we don't want this to affect the speed. So we want to use the base speed. That makes nice effect because when the helicopter is taking off, then the rotor is going to rotate faster, the main rotor. To do that, we use a max function. And we use the second, we leave the second value as 0. So basically this is going to be 0 when the speed is negative, and otherwise it's going to use the positive part of the speed. And on the right and left speed, we're going to do the same and also use abs. Okay. Now these 3 values, which we have determined, so these are the 3 speeds, we're going to sum them up together. So I've added the sum node by pressing the plus, and then I'm adding another pin to sum the third one. And actually we need the 4th pin, because if there is no input, all these speeds are 0, and then we have no rotation of the main rotor. So we also need a value which gives the base rotational speed of the main rotor. So let's right click on this 0 and do a promote to variable. And we are going to call it, and I'm going to rename it here by pressing F2, main rot base speed. Okay. And you can determine its value, a bit by try and error, and depending on what you like. But After you compile and save, you can give it a default value, and I would like to give it a value of 400 because that's what I think works fine for me. And then let's compile and save again. Now what we're going to do with this sum is to use it to drive then the rotation of the main rotor. To do that, we're going to first multiply it by delta seconds, which we have directly out of this value. So I'm going to drag out of delta time x and then press asterisk and then connect them. And then this is basically a delta angle. Now what we want to do is to add this delta angle to a variable which tracks the current rotational angle of the rotor. So we're going to create it. So we go under variables, click plus, and then say main rot angle. So that's the current angle. Make sure that is float. And then we want to drag it here and do a get and sum this. So we have the current angle plus the delta angle given by the combination of this rotational speed times the delta time, which gives again a delta angle. We want to do a modulo of this value, and I'm going to press the percentage sign to get the modulo function by 360. So we don't exceed the 0-360 range. And finally, this is going to be the new value of the main rotation angle. So I'm going to drag it onto the execution pin as usual. It gets a set. I'm going to drag it all the way to the right and then connect it to the output. This one maybe goes down a little bit. And now we can compile and save, by the way. And we have the main rotational angle. Okay. Let's do the same, and it's a bit simpler now for the tail rotor. So for the tail rotor, it's basically the same as we said. Let's drag down this a bit because it's too close and I don't like it. So what we are going to do is take again a reference to our helicopter. Use it to retrieve the yaw rotational speed. Get yaw rot speed. We add this speed to the base speed that we want to rotate the tail rotor with. So I have added the plus function, and then I'm going to right click on the second pin, promote variable, and we're going to call this tail rot base speed. And after I compile, I can give it the default value, and I found that the value of 500 works fine for me. And you can play a bit with the values depending on the visual effect that you want to achieve. And now, as usual, we have to take this value and multiply it by delta time. And it's a bit far, and actually I wanted this to be on the second pin, so I'm gonna control and drag it onto the second pin, and now which will reassign it there. And now I need to get another reference to delta time x, which I don't like at all because it's crisscrossing. So maybe we route it up here, and I'm double clicking on the wire to create this reroute pins, and it's not super nice, but it will work for us. So now this is our delta angle, and we create a new variable, which as before is exactly the same. We're going to call it tail rot angle. And we're going to drag it here to do a get. We sum it with a delta angle with a plus add. We do a modulo 360. And you can press the percentage sign to find the modulo function, and remember to put the 360 here. So now we are bringing back the tail rotor angle into the range of 0-360. And now let's drag this tail rod angle variable onto the set here, so it becomes a set as well. Drag it to the right and connect it. Okay. So we have done everything we need to determine the rotational angles of the main rotor and the tail rotor based on the speed and based on also the yaw rotation. What we have to do is apply this rotation to the respective bones so that we start seeing the visual effect. Okay, so let's move to the anim graph. And this is going to be quite simple. We just need the two nodes. So right click and search for transform, modify bone. And once you have it, click on it. Let's deactivate the translation pin, which we don't need. So I'm clicking on this drop down and then clicking on expose the pin because we don't need it. And it's the same for the scale pin. We could also deactivate the alpha pin, but I like to keep it in general. Now that we have the node with the two pins, we don't need deactivated. Let's Control W to duplicate it because we're gonna need one for the main rotor and one for the tail rotor. Since we are at it, let's connect them to the output pose so that it creates automatically this component to local node. Let's connect these two together, and yeah, this one can be empty. We don't have a reference pose, so that's fine. The other thing we need to do is split these two, the rotation pins. So right click and split struct pin. Let's do the same also for the other. I could have done it earlier, but that's fine. And now the first one we added, we want to use it for the main rotor. And remember that the main rotor, we checked this earlier, but we can check it again, is rotating around its Z axis. Okay, so if I go to the skeletal mesh, click on the main rotor, and then click on the select and translate object, you see that the axis pointing up is the blue axis, which is the Z axis. And the tail rotor, the axis along the direction of rotation is the green axis, which is the yaw one. Which is the pitch one. Okay, so let's drag the main rot angle variable onto the anim graph, do a get, and as we just said, we connect it to the rot yaw, so the rotational Z. And then we take a copy of the tail rotor angle, also drag it and do a get, and this time we connect it to the pitch. Perfect. We haven't told the two nodes yet which bones they need to operate on. So let's click on now the node that we are using for the main rotor and make sure that the bone to modify its main rotor. And then under rotation, we want to say replace existing. And we also want to use bone space. Compile, and you already see that the base speed is making the rotor, the main rotor rotate. Let's do the same for the tail rotor. So bone to modify, tail rotor, rotation mode, replace existing, rotation space, bone space. Let's compile. And we already see the two rotors rotating according to the respective base speed. And of course, there is no input, so there is no variation. But it's time to go back then to the level and check how this is working. So I'm going to compile and save. Close the anim graph and press play. Okay, so now we have our rotors rotating. Now, if I press the up key to go up, you will see that the main rotor starts to speed up a bit faster. And also if I use the yaw, you will see so if I use the right key to yaw clockwise, you will see a slight change in the speed of the tail rotor. So it's speeding up if I do a clockwise rotation, and it's kind of slowing down if I do a counterclockwise rotation. And also if I now translate left and translate right, you see that increase in speed, as well as if I move forward and if I move backward. Okay, so that makes for a nice effect. So we have the inclination, we have the animation of the rotors also depending on the speed. We have also the tail rotor animating depending on the yaw rotation. And we can control our helicopter pretty nicely. And we can land not super center. Well, the reason that I couldn't center it properly is that I'm not really seeing, the front because I cannot rotate my spring arm. So let's do that quickly. It's a final touch. So escape, let's reopen our blueprint. And now let's go here on the right side of all our inputs and add right click, look right. And let's also add the right click, look up. And now we drag from the components our spring arm, do a get, and then we can drag out of it and say add relative rotation. Let's split the delta rotation pin, split struct pin, and then click on it, Ctrl W to duplicate. And we take it down here. We connect the respective execution pins, and we connect also the spring arm to this one. And now the look right is the yaw, and the look up is of course the pitch. So now we can control with our mouse the spring arm. So let's compile and save. Close, play. And now as you can see, I can rotate around my helicopter. And remember that we decouple the rotation of the spring arm from the rotation of the helicopter. You can check that out and maybe restore it. Maybe you like it differently. And anyway, we can now, while we are in flight, also rotate around our helicopter. So now I can follow it also with the camera, which makes it probably easier to land onto my platform. And of course, here we are. Okay, that's it for this tutorial. I hope you have enjoyed. Again, if you want the full project with also the engine sound added, you can find the link in the description. It's available for a small fee. Thanks for watching and see you in the next tutorial. Bye!